Good afternoon friends. Today we will discuss three continuous distributions, namely Quasi distribution, Weibull distribution and Laplace distribution. So let us start with Quasi distribution. Professor Gothi will discuss the Quasi distribution and its characteristics.
Okay friends, first I start with the Quasi distribution. So first of all we take definition. A continuous random variable x is said to follow standard Quasi distribution if its probability function is given by 1 upon pi into 1 upon 1 plus x square, where range of x is from minus infinity to infinity and 0 otherwise. So this is the PDF of standard quasi-variate, and in that case random variable x is said to be standard quasi-variate. Here if we take, say, x is equal to y minus mu upon sigma, then we shall get the PDF of y, and it is, say, gy is equal to 1 upon pi into 1 upon 1 plus y minus mu upon, instead of sigma I just take lambda because sigma is standard notation for standard deviation. So, and if we simplify this into Jacobian, so that is 1 upon lambda, dx is equal to 1 upon lambda dy. So this is equal to lambda upon pi into 1 upon lambda square plus y minus mu square, where y is from minus infinity to infinity, mu is also from minus infinity to infinity, and lambda is positive and 0 otherwise. So this is the PDF of quasi-variate with two parameters, mu and lambda. Mu is the shape parameter, whereas lambda is a scale parameter which is always positive. From this now I just want to find mean and variance of this Quasi distribution. So if you want to find mean, say mean mu and dash, say, that is expected value of y, that is integral over the range, total range is from minus infinity to infinity, y gy dy is equal to lambda upon pi integral y upon this lambda square plus y minus mu square dy. To obtain this integral, let us add and subtract subtract and add mu. So y minus mu plus mu. So this is equal to lambda upon pi into integral y minus mu upon lambda square plus y minus mu square dy plus lambda into integral from minus infinity to infinity 1 upon lambda square plus y minus mu square dy. I just write this integral as, say, I suppose, plus lambda into, if we integrate this, then it is 1 upon lambda tan inverse y minus mu upon lambda. It is of the type 1 upon x square plus a square type. So integral is 1 upon a tan inverse x upon a type. So where this I is equal to integral minus infinity to infinity y minus mu upon lambda square plus y minus mu square dy. So this is lambda upon pi into I plus this lambda is cancelled, and tan inverse infinity is pi by 2, and tan inverse minus infinity is minus pi by 2. So this is pi, there is 1 lambda upon pi is there. So 1 upon pi, I just, this mu is there, mu
Second term.
mu into lambda by pi. So mu, so this is lambda upon pi into I plus mu, pi by 2 plus pi cancel, so mu plus this. Now actually the only problem is to obtain the value of I, and to obtain I, actually if it multiply and divide by 2, then we can get log of denominator type, and log of infinity and log of minus infinity are undefined, and therefore this definite integral does not exist. It is not a specific, so this is not absolutely convergent, and therefore we can say that mean does not exist, and therefore we shall go for its principal value. To find this, we take this way, say limit n tends to infinity, integral from minus n to n, y minus mu upon lambda square plus y minus mu square dy. So ultimately when we take limit as n tends to infinity, so it becomes minus infinity to infinity. Actually it is not the exact value as I, it is its principal value. So limit n tends to infinity. Now if we obtain its integral value, so if we multiply and divide by 2, then we shall get derivative of denominator in the numerator, and therefore it is log of denominator. So log of L square lambda square plus y minus mu square minus n to n. So this is equal to 1 upon 2 limit as n tends to infinity. This is log of, just replace y by n, then replace y by minus n and take the difference. So log of lambda square plus n minus mu square minus log of lambda square plus minus n minus mu, means I can write n plus mu square. So this is equal to 1 upon 2 limit n tends to infinity. This is log of lambda square plus n minus mu square upon lambda square plus n plus mu square, and so this is equal to, now log and limit can be interchanged, and so log of limit of this, and to find this limit we may take maximum power of n common. So there is one technique to find the limit as n tends to infinity. There are two methods. First method is just to take maximum power of n common from the numerator and denominator, or you may take y is equal to 1 upon n. So here I take maximum power of n common, so n square common, so in the bracket lambda square plus 1 minus mu upon n square, lambda square by n square. Here also n square common, so lambda square by n square plus 1 plus mu by n square. N square cancel, and as n tends to infinity, anything divided by infinity will be 0. So this is 0, these two are also 0, ultimately 1 upon 1 means 1, and log of 1 is equal to 0. So that conventional value of I is 0. So ultimately this is 0, and therefore mean mu 1 dash is equal to mu. So this is not the exact value. Actually mean of this distribution does not exist. But if you go for its principal value, then this is the conventional mean. So if we consider mean as mu, then we can find variance also. So say variance of y, that is expected value of y minus mu square, its conventional mean. So this is lambda upon pi y minus mu square gy dy, and therefore this is here, if we add and subtract mu square, sorry lambda square, so lambda square plus y minus mu square minus lambda square upon this. So this is now lambda upon pi into this upon this 1. So integral from minus infinity to 1 dy minus lambda square integral 1 upon lambda square plus y minus mu square dy. Now we know that we can find this value. In the mean also we had this type of integral. But here we cannot find, because integral of 1 is y, replacing by infinity and minus infinity we get infinity. So value is infinite. So if expectation is infinite, means we say that expected value does not exist. So here in this case variance does not exist. Even if we go for its conventional value, principal value, say if you want to obtain this value, principal value of this, so we may write this as limit n tends to infinity, integral from minus n to n dy, say 1 dy, then limit n tends to infinity, integral is y, replacing y by n and minus n, ultimately we get 2n, and this is again infinity. So its conventional value also does not exist. So this way variance also does not exist. So for this particular distribution, mean and variance do not exist. Then we go for its characteristic function, say. So characteristic function, say phi t, I just obtained for a standard Cauchy distribution. So it is expected value of e raised to I t x, that is integral from minus infinity e raised to I t x fx dx, where fx is the PDF of standard Cauchy. So 1 upon pi integral minus infinity e raised to I t x 1 upon 1 plus x square dx. So actually this is a complex integral, and it is the case of contour integral. So actually the contour integrals is not the part of the syllabus up to TY B.sc even, and therefore I just write it is, if you obtain by complex integrals, this value is e raised to minus mod t. Even otherwise also, if characteristic function is this, then by inversion theorem we can find PDF also. So here characteristic function of standard Cauchy is this. Now if you remember, in 12th standard we have studied this, that function fx is equal to mod x, say, is continuous at x is equal to 0, but not differentiable at x is equal to 0. So here it is the same case, it is mod t. So derivative of e raised to minus mod t is not differentiable at t is equal to 0. Generally when we differentiate this and put t is equal to 0, then this value 1 upon I into this will give you first moment mean. But since derivative at t is equal to 0 does not exist, we say that mean of this distribution does not exist. Second thing, if we take, say, x is equal to y minus mu upon lambda, or in capital notation if I write, say, x is equal to y minus mu upon lambda, actually this is the characteristic function of x, standard Cauchy variate. So from this we can get characteristic function of y. So say phi yt, characteristic function of y, that is expected value of e raised to I t y is equal to expected value of e raised to I t, y means mu plus lambda x. So this is equal to e raised to I t mu, which is constant, and expected value of e raised to I t mu x, and therefore this is e raised to I t mu into characteristic function of x with parameter mu t, lambda, sorry, this is lambda. So e raised to lambda t. So this is equal to e raised to I t mu into e raised to minus t lambda. So ultimately it is e raised to I t mu minus lambda is positive. Actually mod t lambda is mod t into mod lambda, but lambda is positive, so mod lambda is lambda into mod t. So this is the characteristic function of Cauchy variate with parameters mu and lambda. Now we want to obtain the distribution of sum of independent Cauchy variates. Suppose we have n in, so we consider this as a theorem. Suppose y1, y2, yn are n independent Cauchy variates such that each yi is Cauchy variate with parameters mu I, lambda I. So all yi's are independent and they all are Cauchy with different parameters mu i's and lambda i's, I running from 1 to n, and we just want to obtain the distribution of sigma yj, j running from 1 to n. So since all yi's are Cauchy variate, as we saw here, the characteristic function of yj, say phi yj, is e raised to it mu j minus lambda j into mod t for all j running from 1 to n. Now if you obtain, actually we have to obtain the distribution of sigma yj. So let us obtain the characteristic function now of sigma yj, that is phi sigma y t. So expected value of e raised to it sigma yj, and if we simplify, this is product j running from 1 to n, expected value of e raised to it yj, because it is e raised to it y1 into e raised to it y2 and so on. Since all yi's are independent, e raised to it yj's are also independent, and therefore expectation of their product is equal to product of their expectations. So this is nothing but product j running from 1 to n phi yj t. So this is equal to product e raised to it mu j minus lambda j into mod t, and so base is same, so powers will be added when we take multiplication. So e raised to it sigma mu j minus sigma lambda j into t, and as we know, this is the characteristic function of Cauchy distribution with parameters sigma mu j and sigma lambda j, and therefore by inversion theorem we can say that the distribution of sigma yj is also Cauchy with parameters sigma mu j and sigma lambda j. Now similarly, if x1, x2, xn are standard Cauchy, are independent standard Cauchy variates, then if you obtain the distribution of its mean 1 upon n sigma xj, say x bar. So if x1, x2, xn are independent standard Cauchy variates, then distribution of x bar is also standard Cauchy. That we can easily prove from this, because all mu j's are same and lambda j's are also same. Now suppose x is standard Cauchy variate, therefore its probability function is 1 upon pi into 1 upon 1 plus x square, ranges from minus infinity to infinity and 0 otherwise. Now I wish to obtain the distribution of x square. I call it y, say distribution of x square. So the distribution function of y is equal to x square is, say f y y is equal to probability that y is less than or equal to y. That means probability that x square is less than or equal to y, means probability that minus root y is less than or equal to x is less than or equal to root y. So to find the probability we have to just integrate the standard density function of standard Cauchy, that is 1 upon pi 1 upon 1 plus x square dx over the range this minus root y to root y, and as you know this is even function of x, and therefore we can write 2 times 1 upon pi integral from 0 to y 1 upon 1 plus x square dx. So this is equal to 2 upon pi integral is tan inverse x 0 to root y. So 2 upon pi tan inverse root y minus tan inverse 0 means 0. So this is the distribution function of y is equal to x square. Now if we differentiate this with respect to y both sides, then we shall get PDF. So the PDF of y is equal to x square is, say, gy is equal to derivative of fyy. So 2 upon pi is constant, derivative of tan inverse, that is 1 upon 1 plus y square of root y, and derivative of root y is 1 upon 2 root y. So 2 is cancelled. This is root pi into root pi. This is y raised to minus half 1 plus y. So this is gamma half, root pi means gamma half, 1 means I can write gamma 1. This is y raised to half minus 1, and 1 plus y raised to half plus half. Say, so this is 1 upon beta half half. Then y raised to half minus 1, 1 plus y raised to half half. So actually this is the PDF of beta type 2 distribution with parameters half and half. Of course we have to take this distribution afterwards. So if x is a standard Cauchy variate, then distribution of square of x is again beta type 2, and range of y will be from 0 to infinity. One other result, suppose x is normal 0 1, y is normal 0 1, x and y are independent. So we consider two independent standard normal variates. In last 2 sessions we have studied this normal distribution. Now I just wish to obtain the distribution of x upon y. Distribution of x upon y, I call it, say, u. So we want to derive the distribution of ratio of two independent standard normal variates. Now both are standard normal. So say PDF of x is 1 upon root 2 pi e raised to minus half x square. PDF of y, say I denoted by f2y, that is again 1 upon root 2 pi e raised to minus half y square. Here range of x and y both are from minus infinity to infinity. Since they are independent, their joint property function is equal to product of their marginal property functions, and therefore it is 1 upon 2 pi e raised to minus half x square plus y square. Range is from minus infinity to plus infinity. Now to obtain distribution of u, which is x upon y, just take transformation u is equal to x upon y and say v is equal to y. That is x is equal to uy means uv and y is equal to v. Here u and v both will be from minus infinity to infinity. Now if we find Jacobian, say j, that is dxy duv, this is Jacobian of the transformation, that is dx by du, dx by dv, in the determinant dy by du, dy by dv. So dx by du is v, dx by dv is u, dy by du 0, dy by dv is 1, so ultimately v. And therefore, if we obtain the joint property of u and v, GUV is equal to 1 upon 2 pi integral, e raised to minus half x square means u square v square plus y square means v square and into mode of Jacobian, mode v. Here again u and v both are from minus infinity to infinity. Now if we want property function of u, then we have to integrate this over v. So the marginal PDF of u is, say I write it g1u is equal to integral over v. V is from minus infinity to infinity, GUV du dv is equal to 1 upon 2 pi integral GUV means e raised to minus half v square common in the bracket u square plus 1 more v dv. Now this is even function of v. Integral is over v and therefore it becomes 2 times. So it becomes 1 upon pi 0 to infinity e raised to minus half v square u square plus 1 into mod v dv, but mod v is equal to v when we take range v as from 0 to infinity. Now to obtain this integral, you take say 1 upon 2 v square into u square plus 1 is equal to say w. If we integrate, then 2v dv, 2v into e square plus 1 is equal to dw. So this is equal to 1 upon pi 0 to infinity, and this is e raised to minus w, and v dv means dw into u square plus 1. So 1 upon pi, this is range of v. So as far as v is concerned, u square plus 1 is considered as constant and therefore it can be taken out. Integral of e raised to minus w is minus e raised to minus w 0 to infinity. So when we put w is equal to infinity, e raised to minus infinity is 0, minus 0, minus minus plus, putting w is equal to 0, e raised to 0 is 1. So ultimately this is 1 upon u into 1 upon u square plus 1. Range of u is from minus infinity to infinity, 1 upon pi. So this way, which is the PDF of standard Cauchy. So this way u is a ratio of two independent standard normal variates. So the distribution of ratio of two independent standard Cauchy variates is again standard Cauchy. So now I request Professor Chaudhary to discuss some Laplace distribution, variable distribution and their applications. Chaudhary sir.
So variable distribution is again continuous distribution, and the definition is a continuous random variable capital X is said to have a variable distribution with parameters alpha and beta if the density function is given by this particular form: fx alpha beta equal to beta upon alpha into x upon alpha raised to beta minus 1 into e raised to minus x upon alpha raised to beta, where x is positive, alpha beta both are positive, and the density function is 0 otherwise. Now here in variable distribution there are two parameters, alpha and beta. So alpha is called the scale parameter and beta is called the shape parameter of the distribution. And in the original variable distribution, if we take beta equal to 1, then we get the corresponding distribution, that is exponential distribution. So exponential distribution is a particular case of variable distribution Now let us find the distribution function of Weibull distribution. The cumulative density distribution function of Weibull distribution is, so this is the definition of distribution function, that is fx equal to probability x less or equal to x, that is probability integration over range 0 to x on density function. Now in this integral, if we transform this x upon alpha raised to beta by y, then we have, if we differentiate this, then we get beta upon alpha into x upon alpha raised to beta minus 1 dx equal to dy, and from this transformation the reverse transformation is x equal to alpha into y raised to 1 upon beta, and using that in the previous formula, this particular formula, we get fx equal to integral over this range into e raised to minus y dy, and this is a standard integral, exponential integral. So integrating this and substituting this range, so we have the density function of fx is 1 minus e raised to minus x upon alpha raised to beta. Now the mean and variance of Weibull distribution. So mean of Weibull distribution is alpha into gamma 1 upon 1 plus beta, and the variance is mu 2, that is alpha square into gamma 1 plus 2 upon beta minus alpha square into gamma 1 plus 1 upon beta raised to 2. Now let us find the median of the distribution. So we know that median is the value which divide the whole distribution into two equal parts. So obviously from the distribution function one can easily determine the median of any distribution. So we have fx equal to 1 minus e raised to minus x upon alpha raised to beta. So let m be the median of the distribution. So we have fm equal to 1 half. So using, that means replacing x by m, we get the value of fm equal to 1 half, and after simplification we have the median is equal to m upon alpha, that is equal to log of 2 raised to 1 upon beta, or simply it is median equal to alpha into log of 2 raised to 1 upon beta. Now this is the graph of Weibull distribution. Now if you look at this, here there are two parameters, one is a scale parameter 2.5, other is a shape parameter 1.5. so the graph of Weibull distribution looks like this, and these are various parameter combinations for Weibull distribution. So this is for 1 1, this is for 3.5 and 2, this is for 15 and 6.5, this is for 5.5 and 6.5, and this is for 10 and 10.5. So this is about the Weibull distribution. Now let us discuss one example of Weibull distribution. Now in this case we have the life of a computer processing unit in hours is modeled by a Weibull distribution with parameters beta equal to 2 and alpha equal to 900 hours, and we want to find mean life of computer processing unit, variance of the life of computer processing unit, and the probability that the CPU fails before 500 hours. So let us denote this x. X is a random variable which is Weibull random variable, and it denotes the life in hours of a computer processing unit. So x follows Weibull distribution with alpha equal to 900 and beta equal to 2, and we know the mean of Weibull distribution. So using that formula and putting the value of alpha and beta, we get mean equal to, this is very simple arithmetic, so after simplification we get it is 797.7645 hours. So this is the average life of that computer processing unit. Now let us find the variance. So again we know this formula, and we know the value of alpha is 900 and beta equal to 2. So again after simplification we get the variance of that x is this number, and now let us find the probability. So we know the distribution function of Weibull distribution. So using that distribution function one can easily determine the probability of this type of event, that is probability x less than 500. We want to find probability that CPU fails before 500 hours. That means probability that x, because x is the life of CPU, life in hours of CPU, so probability that x is less than 500. So it is simply using this particular definition function, it is f of 500. So putting x equal to 500, alpha equal to 900 and beta equal to 2, and after simple arithmetic we get that probability equal to 0.265556. So what it indicate? It indicate that, so probability that CPU fails before 500 hours, it indicate that 26.55% of all CPU fails before 500 hours. So this is the real life application of Weibull distribution. Now let us discuss third distribution, that is Laplace distribution. Now again, Laplace distribution is a continuous distribution. It is also known as a double exponential distribution. So there is a reason behind this. So we will discuss that afterwards. It is also known as a bilateral distribution. So the PDF of Laplace distribution is fx mu lambda, that is lambda by 2 into e raised to minus lambda absolute x minus mu, x ranging from minus to plus infinity, mu from minus to plus infinity, lambda greater than 0, and the density take value 0 in other cases. Now in the Laplace distribution, if here mu is called the location parameter. So if you look at the density function, so this mu is called the location parameter and this lambda is called the scale parameter, because the value of mu locate the curve of the distribution and lambda define the shape of the distribution. So mu is a location parameter and lambda is a scale parameter. So in notation one can write it as x follows Laplace distribution with parameter mu and lambda. Now one can easily verify whether this function, because since this is a typical function having absolute value, so one can easily verify whether this function is a probability density function or not. So for the given, for all values of x, this fx mu lambda is always greater than or equal to 0, the first condition for all x, and the second condition, so if we integrate over the entire range and if we simplify, so after simple arithmetic we have this integral equal to 1. So this indicate that this fx mu lambda is a probability density function, that is PDF. Now let us define a standard Laplace distribution. So from the Laplace distribution, if we take mu equal to 0 and lambda equal to 1, then we have a standard Laplace distribution. So the functional form is fx equal to 1/2 e raised to minus absolute x, x from minus to plus infinity. In notation one can write this mu is 0 and lambda is 1, so it is x follows Laplace with 0 and 1. Now the mean and variance of Laplace distribution, so I have dictated here directly, so we will discuss this afterwards. So mu1 dash is mu, that is mean is mu, and the variance of the Laplace distribution is 2 upon lambda square. So these are the graph of Laplace distribution for various parameter combinations. So if you look at this graph, Laplace with 0 2, so 0 is the central value. So if we observe that from the graph, so it is exactly symmetric about 0, right? All the graph are symmetric, right? So this first parameter is mu, so it locates. So if you observe this first graph, that is this graph black and this is green, so I have changed the location. So here the location is slightly different, right? And these are various parameter combinations. So if we change the scale, so in the first graph, this orange graph, blue graph and pink graph, the location is same, right? But the scales are different. So here the scale is 2. Here that lambda is 3, lambda is 7 and lambda is 10. So we have different type of graphs for Laplace distribution for various parameter combination. Now let us find the distribution function. So again the same definition, fx is probability x less or equal to x. So it is integral from minus infinity to x fx dx, and now here there are two cases. Since the range is from minus infinity to x, so depending upon the relation of x and mu. So if x is less than mu, we have absolute of x minus mu is equal to minus x minus mu, and after simple integration, because this is exponential integral, so after simple integration when x is less than mu, the distribution function capital Fx is given by 1/2 e raised to lambda into x minus mu. And the second case, when x is greater than or equal to mu, so in that case this absolute x minus mu is positive, and again same integral, but here since we have to integrate from minus infinity to x, we split it into two parts, minus infinity to mu and mu to x, and for this particular part the value remains same, but for this part it is x minus mu, and again after simple integration we have the distribution function is 1 minus 1/2 e raised to minus lambda into x minus mu. So ultimately the distribution function of Laplace distribution depends on the value of mu. So if x is less than mu, we have this is the functional form of the distribution function. If x is greater than or equal to mu, this is the form of the functional distribution function. Now this distribution function is very useful to find median as well as quartiles, or in general quantiles of the distribution. So let us find the quartiles of Laplace distribution. So this is the distribution function of Laplace, and we have quartiles are the values which divide the whole distribution into 4 equal parts. So there are 3 in number, so q1, q2, q3. So if we define ith quartile as qi, then f of qi equal to probability x less or equal to qi, that is 1 upon I upon 4. So if we take q1, q2, q3 one by one and simple arithmetic, there is a simple arithmetic, so we get q1 equal to mu plus 1 upon lambda into log of 0.5, then q2 equal to mu and median equal to mu, q3 equal to mu minus 1 upon lambda log of 0.5, and let us find the moment generating function of Laplace distribution. So the Mgf is expectation of e raised to tx, and by this integral one can, using this transformation, one can determine the integral, because again this integral is nothing but a simple exponential integral. So the Mgf is given by, after first few simplification steps, we have Mgf is e raised to t mu into 1 minus t square upon lambda square raised to minus 1. Now from Mgf one can define Cgf, because from Mgf one can generate moment, for Cgf one can generate cumulants, and from cumulants one can get the moments, and moments are very useful to describe the data. So if we take the log of Mgf and if we use this simplification, this logarithmic series expansion, so we have Cgf is given by mu t plus 1 plus t square upon lambda square plus t raised to 4 upon 2 lambda raised to 4 plus and so on. And this cumulants, so first cumulant is mu1 dash, that is coefficient of t in the expansion of kxt. So coefficient of t is only mu, so mean of Laplace distribution is mu. Then coefficient of t square upon 2 factorial, so that is 2 upon lambda square. So here we have only lambda square, 1 upon lambda square, right? So if we multiply by 2 and divide by 2, so we get 2 upon lambda square, but this second cumulant is nothing but the variance of the distribution. So variance is 2 upon lambda square. Similarly k3, k3 that is third cumulant, it is again coefficient of t cube upon 3 factorial, and that is mu 3, it is 0. So when mu 3 is 0, it indicates that the distribution is symmetric, and if we observe from the graph, so the Laplace distribution is again a symmetric distribution. If you observe from this, it is a symmetric distribution. It is symmetric at x equal to mu. It is symmetric at x equal to mu. And finally the fourth cumulant, that is mu 4 minus 3 mu 2 square, it is 12 upon lambda raised to 4. So mu 4 is 24 upon lambda raised to 4. Now let us discuss one example. Suppose we have x and y, two independent identically distributed exponential variate with parameter theta. Then we want to find the distribution of x minus y. So x follows exponential theta, y is exponential theta, and both are independent. So we know the Mgf of exponential distribution, that is 1 minus t upon theta raised to minus 1, and the Mgf of y, which is again exponential with same parameter, so it is also same. So let us define u equal to x minus y, and let us find the Mgf of u. So it is mu t equal to expected e raised to tu, and u is x minus y. So, and since x and y are independent, so e raised to tx and e raised to ty, they are also independent. So we have mxt, and here we have my with argument minus t. So the Mgf of x is 1 minus t upon theta raised to minus 1, and Mgf of y is 1 minus t upon theta raised to minus 1. So putting these values here directly, and here by replacing the argument t by minus t, we have 1 minus t upon 1 minus t square upon theta square raised to minus 1. And if we observe this Mgf, it is the Mgf of Laplace distribution. So the Mgf of Laplace distribution is, which parameter mu and lambda is this. So if we compare this Mgf with this Mgf, so mu is 0 and lambda is taken as theta. So if x and y are independent exponential variate, then u equal to x minus y follows Laplace distribution with 0 and theta as a parameter. So friends, we have discussed three distributions: Weibull, Cauchy and Laplace distribution. So these three distributions are very important, and specifically these distributions are used in industrial applications.
સારું મિત્રો, નેક્સ્ટ ટાઈમ આપણે આગળ બીજા ગેમા બીટા ડિસ્ટ્રીબ્યુશન, બીટા ટાઈપ 2 ડિસ્ટ્રીબ્યુશન વગેરેનો અભ્યાસ કરીશું. ઓકે,
નમસ્કાર.
નમસ્કાર.